morning, everyone. I'm Barney from the Budapest University of Technology and Economics, presenting my paper, Controlling 2D Laplacian Eigenfluids. In my talk, I will present to you how we usually do physical simulations real quickly, and then show you how we can make these differentiable. And after that, I will focus on fluid simulations and build up to controlling these fluid simulations. And building up to introducing neural networks for these control problems. So in our physical simulation, we usually have a model of our real world, and we have a state of this system. For example, some initial starting position and some initial velocity. Then we can simulate our system forward in time. And it's important to note here that in our simulation, the state of our system in the next time step is given as a function of the previous state of our system in the previous time step. And then once we run our simulation, we can observe our system and compare it against some target outcome. For example, did the ball land in the chair or did it not? And this will be the key to making our physical simulations differentiable. Let's imagine that the ball did not land in the chair, but instead landed at position xn after the simulation finished. And then we can compare it against some expected target outcome. For example, the x star position of the chair, and we can write a loss function between these two states. In the easiest case, the distance between these two positions. And then, if we can calculate the derivatives of our loss function with regard to, for example, the initial states, this will exactly tell us how we can modify these parameters in order to reduce our loss and thus reach the target outcome. In order, we can get these derivatives using the good old chain rule, where we can backpropagate through our time steps. And then with these derivatives in hand, we can just iteratively step in the direction of the negative gradient and try to minimize our loss using gradient descent. Our knowledge of our physical world is usually given in the form of partial differential equations, or PDEs, where the time evolution of our system is given as a partial differential equation, where we can also factor out some optional external control force to be applied at the given time step. And then a simulator can step our system forward in time in discrete time increments delta t. And then a differentiable simulator can also calculate derivatives with respect to any parameter in our simulation. So let's look at this in practice. Here we see a fluid simulation where our target is to find some initial velocity field, plotted on the right, which when simulated for 32 time steps, given some initial smoke plotted on the left, the smoke will be advected to some target position, here denoted in red. So initially, this is not a too interesting animation because we initialized our velocity field to zeros, but only after iterating 3 gradient descent steps, we can already see that we managed to get the smoke somewhat closer. And then running 30 gradient descent iterations, we can see that we managed to get most of the smoke in the desired area. Fluid simulation is governed by the navier-stokes equation, which we usually approximate we usually approximate as discretized on grids or with particles. For some comparison to the methods presented later on, here I show a grid-based fluid simulation, where we can see the evolving velocity field and its curl overlaid on the right, and on the left we see some smoke advected as given by its density function. So let's look at what we mean by simulating fluids in a reduced dimensional space. So instead of, for example, grid-based discretization, we can formulate our velocity field as the linear combination of some global basis functions taken with some W base coefficients, which I plot here with bar plot. And then from these base coefficients and linearly combining these with our base functions, we can reconstruct our velocity field and also its curl, which I show in the middle. And in this reconstructed grid representation, we can then use our regular methods to advect some smoke, for example, as given by its density function. Here I am showing you how the base coefficients were evolved. And then comparing the previously shown grid-based simulation as discretized on a 60 by 60 grid. Here we can see the simulation ran in about 33 seconds. And in the reduced dimensional simulation I used, for this example, I used 16 base coefficients. And here we can see that it almost ran 3 times as fast in this extremely simplistic comparison. But the important thing to note is that we kept track of our simulation only using 16 numbers in the case of our reduced dimensional simulation. In their paper in 2012, David et al. Proposed to use the eigenfunctions of the Laplacian operator as these global basis functions. And here I plot the first 16 of these. And here we can see that these are essentially vortices of different spatial frequencies. One of the important key ideas in our paper is that in some domains these Laplacian eigenfunctions actually take a closed form. Actually, we can solve them in a closed form way where we can analytically derive solutions for each position in our domain. And then, if we would like to advect, for example, some particles in our simulation, we don't have to reconstruct our grid at each time step, but instead we can reconstruct our velocity field only partially at these discrete points. Taking the curl of the navier-stokes, we can derive the vorticity equation, and from this, David et al. In their paper also showed that time evolution in the reduced dimensional space actually takes a very simple form, and the fluid simulation reduces to simple linear algebra operations, where the advection term takes the form of a vector matrix vector multiplication, where the CK matrices are constant. The viscosity term becomes pointwise linear term-wise exponential decay, and the external force becomes a scalar in the reduced dimension. So in our paper, we propose to control such Laplacian eigenfluids. First, I will show you how we can optimize for single cases, as introduced earlier via gradient descent, and then I will show you how we can generalize the solutions by learning to control shape transitions with neural networks, where we approximate the external force component of present in our simulation with a neural network, and then optimize for its theta weight. But before that, let's look at the most simple optimization scenario, where we are once again looking for some initial state, more precisely an initial base coefficient vector, as plotted on the left, which, when simulated for 16 time steps and then reconstructed on a grid, it will line up with a reference as given after 16 time steps. In this very simple scenario, we can see that we just using simple gradient descent iterations, we managed to reduce our loss to 0. But increasing the difficulty of this scenario, where our reference is given after 100 time steps, thus greatly increasing the difficulty of this optimization, we can see that we did not manage to reduce the loss exactly to 0, but we still managed to find good enough initial solutions by running some simple gradient descent iterations. We can also define shapes in our domain. In our paper, we define triangles, circles, and squares as given by their density functions. As I mentioned earlier, we have a closed form explicit description of our fluid field, which motivates the sampling of our shapes to increase the efficiency of our simulation. And for example, for transitioning between a triangle into a circle, we approximate this problem with these sampling points. So once again, let's look for some initial base coefficients such that they represent a velocity field in which we advect some particles, which will line up with some target particles, target positions. And this is the results we get. And naturally, we can improve our solution if we optimize for force vector to be applied at each time step of our simulation. But still, we are just focusing on one single solution and use a gradient descent to find a unique solution. Here we see that here the points get advected to the proper places. We didn't use enough sample points to represent our underlying smoke simulation properly. But using more sample points, when we overlay the actual smoke simulation as discretized on a grid and simulated on a grid, so this is just an overlay under the advection of the points, we see that we managed to get the smoke more tightly together. So until now, we have been optimizing for individual problems, but the question arises, could we generate to a range of problems? And yes, as I already hinted at earlier, we can use neural networks to find the generalized solutions, where we define our neural network as taking in our current positions, our target positions, and also our current base coefficients. And from these, from this giving us our force vector to be applied at the given time step. Our architecture is 6 linear layers after each other with ReLU nonlinear activations between them. For training data, we generate random initial and target shapes in our domain and target linear transition between these and use 75 sample points for each shape. And for the training, we generated 1,800 training sequences and 200 validation sequences. Here we can see that we're targeting such transitions. But before we move forward with the training, let's look at an example of overfitting our neural network to one single problem and to verify whether we can actually use this method. On the left, we use 16 basis functions for our simulation, and on the right, we use 36 basis functions for our simulation. And it's interesting to note that using more basis functions does not necessarily mean a better solution. And we ended up training our neural network using 16 basis functions for the following cases. So after training our neural network, we can look at how well it did on training data. Here we plot the the solution that we got for our points, and under it, I just plotted for qualitative evaluation how well it did on the actual smoke simulations that we initially wanted to approximate. We can see that we managed to keep the smoke tightly together and advect it to the proper positions. But naturally, the real question is that how we did on test data. So how did we generalize to data that was not seen previously during training? We can see that in the case of points, we didn't observe any significant overfitting. We managed to get the points to the proper positions, and also we once again managed to get to keep the smoke tightly together and advect it to the proper positions. So to sum up, in our work, we combined differentiable physics with reduced order modeling, which resulted in a method that was much faster than previous methods, which naturally stems from the simple fact that we describe our system with fewer numbers and also use an efficient simulation technique. And we also observed a regularization effect, which we think was due to the constraints introduced from our reduced dimensional simulation. And it's important to note that these methods presented here trivially scale to 3D, which we are really excited to work on in the near future. And as a closing thought, the lesson here is maybe that looking for an effective representation is often worth it, because sometimes less is more. And naturally, the code is available on GitHub, and you can run all of the examples shown here and retrain the neural networks and also generate these animations that I showed here in Jupyter or Google Colab notebooks. Thank you for your attention.
Great, thank you very much. Are there any questions from the audience? Yeah.
Trivially scales to 3D.
Yes.
But do you consider that, could there be some issues with the learning part of the, I don't know if you, was it related to learning or just the model itself?
Yes, yes, so actually I don't think there would be a problem with learning. I think because so for our simulation we use the reduced dimensional space. So this is just a vector of 16 numbers that tells you how strong each vortex should be. So if we stay in this reduced dimensional space, it doesn't really matter whether it's 2D or 3D, but once reconstructed to our usual grid, and then if we advect some smoke there, which is the initial problem that we would like to solve, then there might be some issues, but I don't really see how that could be, because as I also cited in our paper, there like this simulation technique has been shown to work well in 3 dimensions, and also we have the same explicit description of our velocity field of our basis functions also in 3 dimensions, which is really similar to the description in 2D. So we don't expect to see any difficulties in this regard.
So how many basis functions do you expect? Like, what is the increase to going to 3D in terms of like basis functions that are required to kind of describe the system accurately? Or like
so this is a really interesting question, and the simple answer is that we can use however many basis functions, because actually the error that we acquire in this reduced dimensional simulation is actually very well defined, because simply we can't simulate smaller vortices than the smallest vortex that we use. So it just depends on how well would you like to be able to reconstruct your velocity grid. So for example, if you would just like to find some, I think what's really exciting is maybe you can get some initial parameters for like further optimization with more precise methods, and use this method, for example, to find a coarse approximate solution using fewer basis fields. So what would be really interesting further is to start our optimization using fewer basis functions, get an approximate solution, and maybe move up to more precise to a more precise simulation using more basis functions. But I think it has been shown in other papers that even using low number of basis fields results in surprisingly good results. It's all dependent on what you would like to achieve. What's your use case?
Okay, thank you. A very interesting presentation. So
Thank you.
You had another question?
Yeah, I would like to ask. Thank you. Yeah, one question was already answered, but I have another one. So at the end, you were showing how you can adapt to examples that were not used for the training. So how is the method robust to different shapes? Because you were using, I think, the same shapes
Yes.
as you use for the learning. So I would say different distributions of the targets and the origins, and the size of these distributions, because these seem to have the same size and shapes.
Yes, they do have the same size and shapes. Still, naturally, we were careful to use the same to use like out of distribution generation of shapes for training and then validating it. But yes, that is. So it's really exciting to say that these have not been previously seen. But for training, we use the same shapes with the same size. That's true.
And if you use different shapes and sizes, you think it would still generalize, or it would break down?
So actually, it's a really good question, and we also look forward to improve how we sample these shapes. So actually, we don't consider the shapes for our solution, but as you can see, the actual optimization takes part in this description of our shapes. So these are essentially points. So we don't really expect to. So actually the way we sample shapes, a circle and a square is fairly similar. So if we would like to like more precisely match the target shape, then we would have to use some other techniques, or maybe use some further sample points, something like that. So if that's the use case that we would like to go for, then yes. So yes, that's an interesting question. But other than this, as the actual optimization takes like considers only the position of the point, there won't be any problem, most probably, for other shapes. But yes, it would be interesting to see.
Okay, thank you.
Great. So I think we have to move on to the second talk. So let's thank the speaker once more.
Thank you.